Bismillah ar-Rahman ar-Rahim. Ladies and gentlemen, today's second week is starting, and in second week I have covered classification of all type of positive displacement machines. Hello, if you can't hear me, please unmute your mic and talk to me. If you have any problem, please unmute your mic and talk to me. And after talking to me, please mute it again. Now, please reply to me. Are you hearing me? Can you hear me? Please reply. Unmute your mic and reply.
Yes, sir.
Okay. Can you see this screen?
Yes, sir.
Yes, sir.
Okay. My lecture notes are on the screen, so I'm sharing my screen. But you, okay. Now you please unmute. Everybody unmute your speaker, your mic icon in the Zoom. When you need to talk to me, you can unmute by clicking it, then talk to me, and after talking to me again, unmute. Keeping it on make disturbance. Now, Bismillah ar-Rahman ar-Rahim, in front of you is a figure 12.19. My today's topic is positive displacement machine, that is reciprocating compressor. We have done all about reciprocating compressors. This is the last topic, which is thermal analysis or heat transfer analysis of two-stage compressor with intercooling. LP is the lower stage, HP is the higher stage, low pressure stage, high pressure stage. After low pressure stage, compressed air is hotter at pressure P1, PI, TI, and it enters into intercooler. In intercooler, we circulate cooling water, which takes away heat, and it cools down again to P1, PI and T1. Temperature TI, intermediate pressure, again reduced to T1, initial temperature. So from T1, again compressed air enters into high pressure stage, and its temperature increases to T2. Now, applying each stage, each box here shown, LP, intercooler, HP. So these represent one open system, where mass is entering, mass is leaving, mass is entering, mass is leaving. Entering conditions at this device, LP stage is P1, T1. Leaving condition is PI, TI. I means intermediate. One is suction or induction. And again, this is pressure is same in intercooler PI, but temperature is reduced to T1. Then PI, pressure PI and T1 is entering condition to the high pressure stage. This is also open system, and it is steady flow energy equation will be applied, and we will calculate heat transfer QH, this Q intercooler QI and QL. Q dot L in low stage compressor, cooling water is circulating in the cylinder jacket. In high pressure compressor, cooling water is circulating in the jacket. So heat taken by cooling water in the cylinder jacket is QL and QH, and QI is the heat taken away by the intercooler. Intercooler is again a heat exchanger between two stages, and it also water is circulating in it. Now, from this figure, we'll do the analysis of first law of thermodynamics, which you have learned in Thermo 1, and that is this steady flow energy equation. This is equation 110, and this is written here. And H1 and 1 and 2 conditions are in and out. So H1 plus C1 square by 2 plus Q plus W is equal to H2 plus C square by 2, because there is kinetic energy also here, rho Gz, but rho Gz at inlet and outlet is same, so it is cancelled. So we assume that there is no change in the height. So kinetic energy at inlet, kinetic energy at the outlet can also be ignored, because velocity entering must be equal to approximately velocity leaving. So kinetic energy change will also not take place. So this first law equation of steady flow is converted into very simple equation for QL for low pressure stage, and this is MCP T1 plus QL plus WL is equal to MCP T1. In this equation, kinetic energy, potential energy is ignored. So from here, QL is unknown. We want to calculate Q dot L. So that is heat transfer to the low pressure cylinder. When heat transfer to the low pressure cylinder, can be calculated by this formula Q. Q dot L is equal to minus W dot L minus M dot Cp Ti minus T1. Because this charge outlet temperature is Ti, inlet temperature is T1. I means intermediate between stage 1 and 2. Now heat rejected QL in low pressure stage is WL minus M dot Cp Ti minus T1. This is equation 1224. Now what this is what happens in low pressure stage of the cylinder. What happens in intercooler? After discharge from low pressure cylinder, air enters into the intercooler. So entering condition of the intercooler is also an open system, and mass in, mass out is equal. So P entering condition here is I and outering condition is 1. So PI is equal to P1. So we can take PI here and PI here, but Ti is not equal to T1. So Ti is equal to inlet is Ti, outlet is T1, because there is a condition in the problem. It is given in the derivation that the word is used complete intercooling. The word complete intercooling means temperature at the outlet of intercooler is same as temperature at the inlet to the low pressure state, that is T1. So here T outlet of the intercooler is T1. So now applying energy equation, first law of thermodynamics, steady flow energy equation, energy in is equal to energy out. Energy in is equal to M dot Cp Ti plus Q dot 1. Energy out is equal to M dot Cp T1. So from here, what is unknown is kept to the left and all other will come to the right. So here Qi, that is heat rejected in the intercooler, is equal to minus Cp M dot Cp Ti minus T. It is minus shows that it is heat rejected. This minus sign is removed here because we have added the word heat rejected. Heat rejected in intercooler means this is minus. That's why this minus is not required here. So M dot Cp Ti minus T1 is the heat rejected. So this is equation 1225. After that, air enters. After intercooler, air enters to the high pressure stage. So inlet condition to high pressure stage is Pi and T1. We have just seen, and outlet condition is P2, T2. So WH is the work input and QH is the heat input. We are showing heat input. Actually, it is heat rejected. So this will be shown by the sign. If result is minus, as you will see, that means heat is rejected, and this arrow should be outward. But initially, we show inward. Now, air energy in is equal to energy out. You see, this is in, this is in, this is out, this is out. So we have three in and 1 out. So M dot Cpt1 plus Q dot H plus WH, these are in. So it will come on the left side. Out, energy out is equal to only 1. This is M dot Cpt2. So M dot, so QH, we need calculate QH. It is heat rejected in the high pressure cylinder. Then we say, we keep it left side and we bring other terms on the right side. So we get W dot H minus MCP multiplied by T2 minus T1. And minus sign shows that heat is rejected. So now we write the sentence, heat rejected in high pressure stage is equal to, without minus sign, because rejected means minus. So W dot H minus M dot Cp multiplied by T2 minus T1, this is question 1226, derived with the help of the steady flow energy equation applied on open flow system. And work done in each stage, we have calculated already in previous lectures. W low pressure stage must be equal to W high pressure stage for minimum work input, because and when we have to balance the load on both the cylinders, and we have to divide the pressure ratio equally in 2 stages. So then this is the condition: low pressure work or power must be equal to high pressure. And this we have derived already in previous lecture, n upon n minus 1 multiplied by m dot r T2 minus T1. So this is how we have arrived at this equation. So now numerical problem related to this topic is example 12.8. This is here, and I will give you as a homework, and I will give you all my previous lectures, including homework, and you will do it at home and submit it with your own handwriting. You will write everything in your own handwriting and give it to me. So while doing this, do calculation by yourself. They are calculated, result is there, but everything you should do with your own calculator, with your own handwriting. Don't try to just copy. If there is something not understandable, then you must read again and try to learn it. Now, example 12.8 is using the data in example 12.6, determine the rate of loss to the cylinder jacket, cooling water, and rate of heat loss to the intercooler. So here I have analyzed this. So previous example की जो सारा result outcome है वो यहाँ उसको repeat करना जरूरी है, because book में ये नहीं है. ये मैंने उसकी summary निकाली है. Example 12.5 का data हमें चाहिए, क्योंकि उसने repeat नहीं किया है. Example 12.6 को repeat करने के बजाय उसने कहा कि उसका data use करो और अब बताओ heat rejected कितना होगा in intercooler. So वो सारा डेटा पहले लिखेंगे और उसके बाद ये फार्मूला वगैरह लगाकर you will calculate QL, then QH, and then QH is equal to QL. So you will calculate QI, which is heat rejected in the intercooler. So after that there is a discussion. इसको समझ लें, और वो discussion ये है. The sum of WL/WH इस यहाँ डॉट मैंने नहीं लिखा है बिकॉज उसको लगाना है वर्ड में जरा मुश्किल है, तो with W dot and W bracket में लिख दिया. So the sum of WL dot and WH dot, that is work power in low pressure stage and high pressure stage, is the power extracted on air inside the compressor. ये जो work calculation है वो साइकिल ड्रॉ करके हम कैलकुलेट करते हैं. थर्मोडायनेमिक्स 1 की फर्स्ट लॉ थर्मोडायनेमिक्स के लॉज लगाकर कैलकुलेट करते हैं, और पॉलीट्रॉपिक, आइसेंट्रोपिक, आइसोथर्मल प्रोसेस अज्यूम करके कैलकुलेट करते हैं, जिसके फार्मूले हमने पहले डिराइव कर लिए थर्मो 1 में, चैप्टर 3 में, वो यूज करते हैं. तो ये दरअसल इट इज वर्क डन ऑन द एयर इनसाइड द सिलेंडर. नाउ दिस एनर्जी इज कंज्यूम्ड to increase the pressure and temperature of air. Then actual power exerted by motor on the compressor is equal to the power consumed on air plus power to overcome friction in compressor. Compressor में friction भी होती है, piston ring cylinder के साथ रगड़ खाते हैं, और bearings वगैरह shaft के अंदर bearing चल रही होती है, तो उसकी friction होती है. हालांकि lubrication, इसको कम करने के लिए हम lubrication इस्तेमाल करते हैं, फिर भी friction loss होता है. So उस फ्रिक्शन को कम किया जा सकता है, खत्म नहीं किया जा सकता. तो एक्चुअल वर्क वो नहीं है जो कि आपके थ्योरेटिकल फार्मूला बताते हैं कि सिलेंडर में कितना वर्क आपने किया. सिलेंडर के अंदर जो फ्रिक्शन हुई वो इसमें शामिल नहीं है, लिहाजा वो जो थ्योरेटिकल वर्क कैलकुलेटेड बाय साइकिल एनालिसिस, उसमें फ्रिक्शन वर्क ऐड होता है. फ्रिक्शन वर्क को कैलकुलेट नहीं किया जा सकता, सिर्फ उसकी मोटर की जो एक्चुअल पावर कंज्यूम हुई है वो हम देख सकते हैं मीटर रीडिंग से कि भाई कितने वोल्ट कितने एम्पीयर कंज्यूम हो रहा है. वो लेबोरेटरी में होता है, और उसकी अगर प्रॉब्लम में दे दिया जाता है कि भाई इस कंप्रेसर की एफिशिएंसी कितनी है, तो उस एफिशिएंसी में वो फ्रिक्शन लॉस शामिल होता है. तो या फिर बता दिया जाता है कि भाई मोटर इतने पावर ले रही है और सिलेंडर में इतना वर्क चाहिए, तो बताइए उसकी मैकेनिकल एफिशिएंसी क्या है या फ्रिक्शन लॉस कितना है. लेकिन यहाँ ये मकसद नहीं है, यहाँ आपसे कहा जा रहा है कि आपको फ्रिक्शन लॉस भी वो उसमें शामिल करना होगा. फ्रिक्शन पावर इज कन्वर्टेड टू हीट एनर्जी, ये हीट भी उसमें ऐड होती है. तो हमने जो हीट कैलकुलेट की है इंटरकूलर में, ये वो हीट नहीं जो खाली सिलेंडर में पैदा होती है कंप्रेशन की वजह से, वो फ्रिक्शन की वजह से जो हीट पैदा होती है उसका तकरीबन आधा तमाम फ्रिक्शन जो है वो वर्क डन है इट इज लॉस्ट इट इज नॉट achievable because it is lost it is converted into heat and heat is lost heat cannot be converted into work which is due to friction so friction heat cannot be converted into work friction work is not usable so this is converted into heat loss so about 50% of friction heat goes to the cooling water over and above the heat transferred by the air to the cooling water so after this so this discussion we'll go to next topic so now